Concrete component, basic ingester. Create a concrete class basic ingester that implements the core ingestion logic. Python. Class basic ingester, data ingester. Def ingest, self, data. Print, f, basic ingestion, data. Hashtag perform core ingestion logic here. Return data. Decorator, ingester decorator. Define an abstract decorator class ingester decorator that also implements the data ingester interface. This class will hold a reference to the component it decorates. Python. Class ingester decorator, data ingester. Def underscore underscore init underscore underscore, self, ingester. Self.ingester equals ingester.
Def ingest, self, data. Return self.ingester.ingest, data.
Concrete decorators, validation and logging. Create concrete decorator classes validation decorator and logging decorator that add validation and logging functionalities, respectively. Python. Class validation decorator, ingester decorator. Def ingest, self, data. If self.validate, data. Return super.ingest, data. Else. Print, validation failed. Return none. Def validate, self, data. Hashtag perform validation logic here. Return isinstance, data, dict, and ID in data. Class logging decorator, ingester decorator. Def ingest, self, data. Print, f, logging, ingesting data, data. Result equals super.ingest, data. Print, f, logging, ingestion complete. Return result. Usage. Python. Hashtag create a basic ingester. Basic underscore ingester equals basic ingester. Hashtag decorate with validation and logging. Validated underscore ingester equals validation decorator, basic underscore ingester. Logged underscore validated underscore ingester equals logging decorator, validated underscore ingester. Hashtag ingest data. Valid underscore data equals ID, 123, value, test. Invalid underscore data equals 1, 2, 3. Logged underscore validated underscore ingester.ingest, valid underscore data. Logged underscore validated underscore ingester.ingest, invalid underscore data. Hashtag you can also use just one decorator, or none at all. Logged underscore ingester equals logging decorator, basic underscore ingester.
Logged underscore ingester.ingest, valid underscore data.
Basic underscore ingester.ingest, valid underscore data. Benefits. Flexibility, validation and logging can be added or removed dynamically by wrapping or unwrapping the core component. Open/closed principle, the core ingestion component is closed for modification but open for extension through decorators. Single responsibility principle, each component and decorator has a specific responsibility, making the code easier to understand and maintain. Reusability, decorators can be reused with different ingestion components. Dynamic configuration, the data engineer can create configuration files, or use environment variables to determine which decorators should be applied. Facade pattern use case, simplifying data warehouse interactions. Imagine a data engineer working on a data platform that involves interactions with a complex data warehouse system. This system includes various subsystems like data extraction and loading, ETL handling data ingestion from multiple sources, query optimization, tuning queries for performance, data governance and security, managing access controls and data lineage, metadata management, maintaining data dictionaries and schema information. Problem. Complexity for users. Directly interacting with these subsystems requires users, analysts, data scientists, to understand the intricacies of each component, making it overwhelming. Code duplication. Users might repeatedly write similar code to perform common tasks, leading to redundancy and maintenance issues. Abstraction and encapsulation. Exposing the inner workings of the data warehouse system can make it difficult to modify or evolve the system without breaking existing user code. Solution. Using the facade pattern. The facade pattern allows the data engineer to create a simplified interface, facade, that hides the complexity of the underlying data warehouse subsystems. This facade provides easy-to-use methods for common tasks, abstracting away the details of the individual components. Implementation. Subsystems, complex components. Implement classes representing the various subsystems of the data warehouse, example ETL subsystem, query optimizer subsystem, governance subsystem, metadata subsystem. These classes encapsulate the complex logic of each subsystem. Python. Class ETL subsystem. Def load underscore data, self, source, table. Print, f, loading data from source into table. Hashtag complex ETL logic. Class query optimizer subsystem. Def optimize underscore query, self, query. Print, F, optimizing query, query. Hashtag query optimization logic. Class governance subsystem. Def apply underscore access underscore control, self, user, table. Print, F, applying access control for user on table. Hashtag governance logic. Class metadata subsystem. Def get underscore schema, self, table. Print, F, retrieving schema for table. Hashtag metadata retrieval logic. Return columns, ID, name, value. Facade, data warehouse facade. Create a data warehouse facade class that acts as the simplified interface. This class will hold references to the subsystem objects. It will provide methods for common tasks, delegating the actual work to the appropriate subsystems. Python. Class data warehouse facade. Def underscore underscore init underscore underscore, self. Self.etl equals ETL subsystem. Self.optimizer equals query optimizer subsystem. Self.governance equals governance subsystem. Self.metadata equals metadata subsystem. Def load underscore n underscore query, self, source, table, query, user. Self.etl.load underscore data, source, table. Self.governance.apply underscore access underscore control, user, table. Self.optimizer.optimize underscore query, query. Schema equals self.metadata.get underscore schema, table. Print, F, executing query, query with schema schema. Hashtag execute the query. Usage. Python. Hashtag create a facade instance. DW underscore facade equals data warehouse facade. Hashtag use the simplified interface. DW underscore facade.load underscore n underscore query, data.csv, sales, select asterisk from sales where amount 100, analyst 1. Benefits. Simplified interface, users interact with a single, easy-to-use interface, hiding the complexity of the underlying subsystems. Reduced complexity, users don't need to understand the details of each subsystem, making it easier to perform common tasks. Decoupling, the facade decouples users from the specific implementations of the subsystems, allowing for changes without affecting user code. Improved maintainability, changes to the subsystems are isolated, reducing the risk of unintended side effects. Code reusability, the facade provides reusable methods for common tasks, reducing code duplication. Centralization, the facade centralizes common tasks, making it easier to manage and maintain the data warehouse system. Flyweight pattern use case, handling high-volume time series data with shared metadata. Imagine a data engineer working with a massive stream of time series data from numerous sensors. Each sensor generates data points with a timestamp and a value. However, many sensors share the same metadata, such as sensor type, example temperature, pressure, humidity. Unit of measurement, example Celsius, psi, percentage. Location, example building A, room 101. Problem. Memory overhead, storing this redundant metadata for every data point would consume a significant amount of memory, especially with millions of data points. Performance impact, increased memory usage can lead to performance degradation due to cache misses and garbage collection overhead. Solution, using the flyweight pattern. The flyweight pattern allows the data engineer to share the common metadata, intrinsic state, among multiple data points, reducing memory usage. Implementation. Flyweight, sensor metadata. Create a sensor metadata class that represents the shared metadata. This class will store the intrinsic state, sensor type, unit, location. Make this class immutable to ensure that the shared state remains consistent. Python. Class sensor metadata. Def underscore underscore init underscore underscore, self, sensor underscore type, unit, location. Self.sensor underscore type equals sensor underscore type. Self.unit equals unit. Self.location equals location. Def underscore underscore str underscore underscore, self. Return F, sensor type, self.sensor underscore type, unit, self.unit, location, self.location. Flyweight factory, metadata factory. Create a metadata factory class that manages the creation and retrieval of sensor metadata objects. This factory will maintain a dictionary to store the shared metadata instances. When a new metadata request is made, the factory will either return an existing instance or create a new one if it doesn't exist. Python. Class metadata factory. Underscore metadata equals. At static method. Def get underscore metadata, sensor underscore type, unit, location. Key equals, sensor underscore type, unit, location. If key not in metadata factory underscore metadata. Metadata factory underscore metadata key equals sensor metadata, sensor underscore type, unit, location. Return metadata factory underscore metadata key. Context, data point. Create a data point class that represents a single data point. This class will store the extrinsic state, timestamp, value, and a reference to the shared sensor metadata object. Python. Class data point. Def underscore underscore init underscore underscore self, timestamp, value, metadata. Self.timestamp equals timestamp. Self.value equals value. Self.metadata equals metadata. Def underscore underscore str underscore underscore self. Return f, timestamp, self.timestamp, value, self.value, metadata, self.metadata. Usage. Python. Hashtag create metadata objects using the factory. Temp underscore metadata equals metadata factory.get underscore metadata, temperature, Celsius, building A, room 101. Pressure underscore metadata equals metadata factory.get underscore metadata, pressure, psi, building B, room 202. Shared underscore temp underscore metadata equals metadata factory.get underscore metadata, temperature, Celsius, building A, room 101, hashtag returns existing object. Hashtag create data points. Data underscore point 1 equals data point, 167.888.6400, 25.5, temp underscore metadata. Data underscore point 2 equals data point, 167.888.6460, 26.0, temp underscore metadata. Data underscore point 3 equals data point, 167.888.6520, 15.2, pressure underscore metadata. Print, data underscore point 1. Print, data underscore point 2. Print, data underscore point 3. Print, temp underscore metadata is shared underscore temp underscore metadata, hashtag prints true, they are the same object. Benefits. Reduced memory usage. Sharing metadata objects significantly reduces memory consumption, especially with a large number of data points. Improved performance. Reduced memory usage translates to better performance due to fewer cache misses and less garbage collection. Data consistency. Sharing immutable metadata objects ensures data consistency and avoids accidental modifications. Scalability. The flyweight pattern enables the system to handle a massive volume of time series data efficiently. Centralized metadata management. The metadata factory class provides a central location for managing shared metadata. Proxy pattern use case. Controlled access to a data lake storage system. Imagine a data engineer working on a platform that provides access to a large data lake storage system, example S3, ADLS. Direct access to the data lake can be risky due to potential security vulnerabilities, performance bottlenecks, and resource overuse. The data engineer wants to implement a controlled access mechanism. Problem. Security risks. Unrestricted access could lead to unauthorized data access, modification, or deletion. Performance issues. Direct access might overload the data lake, causing performance degradation for all users. Resource management. The data engineer needs to enforce quotas and usage policies to prevent resource overuse. Auditing and logging. They need to track data access for auditing and compliance purposes. Solution. Using the proxy pattern. The proxy pattern allows the data engineer to create a proxy object that acts as an intermediary between users and the data lake storage system. This proxy can enforce access controls, perform caching, and log access requests. Implementation. Subject, data lake interface. Define an interface or abstract class data lake that represents the data lake storage system. Python. From ABC import ABC, abstract method. Class data lake, ABC. Add abstract method. Def read underscore data, self, file underscore path. Pass. Add abstract method. Def write underscore data, self, file underscore path, data. Pass. Real subject, actual data lake. Create a concrete class real data lake that implements the actual data lake access logic. Python. Class real data lake, data lake. Def read underscore data, self, file underscore path. Print, f, reading data from file underscore path in the real data lake. Hashtag simulate data reading from the data lake. Return f, data from file underscore path. Def write underscore data, self, file underscore path, data. Print, f, writing data to file underscore path in the real data lake. Hashtag simulate data writing to the data lake. Proxy, data lake proxy. Create a data lake proxy class that implements the data lake interface. This class will hold a reference to the real data lake object. It will implement access control, caching, and logging logic. Python. Class data lake proxy, data lake. Def underscore underscore init underscore underscore, self, user, real underscore data underscore lake. Self.user equals user. Self.real underscore data underscore lake equals real underscore data underscore lake. Self.allowed underscore users equals data underscore analyst, data underscore engineer. Self.cache equals def read underscore data, self, file underscore path. If self.user not in self.allowed underscore users. Print, access denied. Return none. If file underscore path in self.cache. Print, f, retrieving file underscore path from cache. Return self.cache file underscore path. Data equals self.real underscore data underscore lake.read underscore data, file underscore path. Self.cache file underscore path equals data. Self.log underscore access, file underscore path, read. Return data. Def write underscore data, self, file underscore path, data. If self.user equals data underscore engineer. Print, write access denied. Return. Self.real underscore data underscore lake.write underscore data, file underscore path, data. Self.log underscore access, file underscore path, write. Self.cache.pop, file underscore path, none, hashtag invalidate cache. Def log underscore access, self, file underscore path, operation. Print, f, user self.user performed operation on file underscore path. Usage. Python. Real underscore lake equals real data lake. Analyst underscore proxy equals data lake proxy, data underscore analyst, real underscore lake. Engineer underscore proxy equals data lake proxy, data underscore engineer, real underscore lake. Random underscore proxy equals data lake proxy, random underscore user, real underscore lake. Hashtag allowed access. Data equals analyst underscore proxy dot read underscore data, data slash sales dot CSV. Print, data. Engineer underscore proxy dot write underscore data, data slash new underscore sales dot CSV, new sales data. Hashtag denied access. Random underscore proxy dot read underscore data, data slash secret dot CSV. Random underscore proxy dot write underscore data, data slash something dot CSV, test. Hashtag cached access. Analyst underscore proxy dot read underscore data, data slash sales dot CSV, hashtag reads from cache. Benefits. Controlled access. The proxy enforces access controls, ensuring that only authorized users can access the data lake. Security enhancement. It adds a layer of security by preventing direct access to the sensitive data lake. Performance optimization. Caching frequently accessed data improves performance. Resource management. The proxy can implement quotas and usage policies to prevent resource overuse. Auditing and logging. It logs data access requests, providing valuable information for auditing and compliance. Decoupling. The proxy decouples users from the actual data lake implementation, allowing for changes without affecting user code. Chain of responsibility pattern use case, data validation and transformation pipeline. Imagine a data engineer building a data ingestion pipeline where incoming data needs to undergo a series of validation and transformation steps. The specific steps and their order might vary depending on the data source or the type of data being processed. Problem. Varying validation/transformation logic. Different data sources or data types require different validation and transformation rules. Flexibility and extensibility. The pipeline should be flexible enough to accommodate new validation and transformation steps without modifying existing code. Decoupling. The logic for each validation and transformation step should be decoupled from the pipeline's overall control flow. Dynamic pipeline configuration. Being able to configure the order and types of validation/transformation steps dynamically. Solution, using the chain of responsibility pattern. The chain of responsibility pattern allows the data engineer to create a chain of handlers, where each handler is responsible for a specific validation or transformation step. The data is passed along the chain, and each handler can either process the data or pass it to the next handler in the chain. Implementation. Handler, data processor. Define an abstract handler class data processor that represents the common interface for all validation and transformation steps. This class will have a set_next method to set the next handler in the chain in a process method to handle the data. Python. From ABC import ABC, abstract method. Class data processor, ABC. Def__init__, self. Self.next_processor equals none. Def set_next, self, processor. Self.next_processor equals processor. Return processor. Add abstract method. Def process, self, data. Pass. Concrete handlers, validation and transformation steps. Create concrete handler classes that implement the specific validation and transformation logic. Python. Class null value validator, data processor. Def process, self, data. If none in data. Print, null value found. Validation failed. Return none. Print, null value validation passed. If self.next underscore processor. Return self.next underscore processor.process, data. Return data. Class type validator, data processor. Def underscore underscore init underscore underscore, self, expected underscore type. Super, dot underscore underscore init underscore underscore. Self dot expected underscore type equals expected underscore type. Def process, self, data. If not all, isinstance, x, self dot expected underscore type, for x in data. Print, f type validation failed. Expected self dot expected underscore type dot. Return none. Print, type validation passed. If self.next underscore processor. Return self.next underscore processor dot process, data. Return data. Class string trimmer, data processor. Def process, self, data. Trimmed underscore data equals str, x, dot strip, if isinstance, x, str, else x for x in data. Print, string trimming applied. If self.next underscore processor. Return self.next underscore processor dot process, trimmed underscore data. Return trimmed underscore data. Class data converter, data processor. Def underscore underscore init underscore underscore, self, conversion underscore func. Super, dot underscore underscore init underscore underscore. Self dot conversion underscore func equals conversion underscore func. Def process, self, data. Converted underscore data equals self dot conversion underscore func, x, for x in data. Print, data conversion applied. If self.next underscore processor. Return self.next underscore processor dot process, converted underscore data. Return converted underscore data. Usage. Python. Hashtag create the chain of handlers.
Null underscore validator equals null value validator. Type underscore validator equals type validator, str.
Trimmer equals string trimmer. Converter equals data converter, int. Hashtag build the chain. Null underscore validator dot set underscore next, type underscore validator, dot set underscore next, trimmer, dot set underscore next, converter. Hashtag process data. Data 1 equals 1, 2, 3. Data 2 equals 1, none, 3. Data 3 equals 1, 2, 3. Processed underscore data 1 equals null underscore validator dot process, data 1. Processed underscore data 2 equals null underscore validator dot process, data 2. This is essential for building robust and reliable data pipelines that can handle failures and retries gracefully. It basically means that the results of a given output will be the same no matter how many times you run it. Merge is an example. It only appends a record where there is no other row that exists with the same ID. An insert appends the row, repeating whatever value that exists in any other rows. Idempotent is important because in stateful events, you don't want to loop a never-ending copying of data. Processed underscore data 2 equals null underscore validator dot process, data 2. Processed underscore data 3 equals null underscore validator dot process, data 3. Print, f, processed data 1, processed underscore data 1. Print, f, processed data 2, processed underscore data 2. Print, f, processed data 3, processed underscore data 3. Benefits. Flexibility, the pipeline can be easily modified by adding, removing, or reordering handlers. Extensibility, new validation and transformation steps can be added by creating new handler classes. Decoupling, each handler is responsible for a specific task, making the code more modular and maintainable. Dynamic configuration, the chain of handlers can be dynamically configured based on data source or data type. Clear responsibility, each handler has a clear responsibility, making it easier to understand and debug the pipeline. Improved code organization, the chain of responsibility pattern promotes organized code and simplifies complex processing workflows. Pipeline or chain of responsibility, for creating a sequence of processing steps, where data flows through each step in a defined order. This is useful for ETL pipelines, data validation, and cleaning workflows. Factory, for creating objects without specifying the exact class of object that will be created. This is helpful for creating data source connections, data formatters, or transformation objects dynamically based on configuration or data characteristics. Singleton, for ensuring that a class has only one instance and providing a global point of access to it. This can be used for managing shared resources like database connections, configuration managers, or logging utilities. Strategy, for defining a family of algorithms, encapsulating each one, and making them interchangeable. This is valuable for implementing different data processing strategies, such as filtering, aggregation, or machine learning model training, and allowing them to be selected at runtime. Template method, for defining the skeleton of an algorithm in an operation, deferring some steps to subclasses. This is useful for defining common data processing workflows with variations in specific steps, such as data extraction or loading. Adapter, for converting the interface of a class into another interface clients expect. This is essential for integrating with different data sources, APIs, or third-party libraries that may have incompatible interfaces. Decorator, for dynamically adding responsibilities to an object. This can be used for adding data validation, logging, or monitoring capabilities to data pipelines without modifying the core processing logic. Facade, for providing a simplified interface to a complex subsystem. This is helpful for interacting with data warehouses, cloud storage systems, or distributed computing frameworks, hiding their complexity behind a unified interface. Composite, for composing objects into tree structures to represent part-whole hierarchies. This is useful for building complex data transformation pipelines or representing hierarchical data structures. Flyweight, for reducing memory usage by sharing objects. This is beneficial when dealing with large volumes of data with repetitive elements, such as sensor data or log files. Proxy, for controlling access to an object. This can be used for implementing security measures, caching, or lazy loading in data access layers. Builder, for separating the construction of a complex object from its representation so that the same construction process can create various representations. This is useful for building complex data structures or query builders. Observer, for defining a one-to-many dependency between objects so that when one object changes state, all its dependents are notified and updated automatically. This can be used for triggering actions based on data changes, such as sending alerts or updating dashboards.
Actually, I want both of you.
Algorithms and data structures.
Hanging out with me, you're gonna talk.
Heaps, these are useful for finding minimum or maximum values, and specifically for finding the top k values 1. A minimum heap can provide the minimum value in O, 1, time 1. Building a heap from a set of n values can be done in O, n, time, but adding each value individually takes O, n log n, time 2. Heaps also show up in graph algorithms 3. Sliding window, this technique uses 2 pointers to iterate through an array, often reducing time complexity from O, n caret 2, to O, n, 4. It's a standard algorithm that can be memorized and applied to many problems for binary search. This algorithm is used to efficiently search for a value in a sorted array 6. It works by repeatedly dividing the search interval in half, resulting in a time complexity of O, log n, which is more efficient than O, n, 7. Identifying when to use binary search can sometimes be challenging. 8. Depth first search, DFS, and breadth first search, BFS. These are common algorithms used in coding interviews that can be applied to trees and general graphs. 9. DFS and BFS are building blocks for more complex algorithms. 10. Mastering these algorithms is essential for coding interviews. 11. Recursion, this is a technique where a function calls itself, and it's used in many areas, including graphs, backtracking, and dynamic programming. 12. It is important to understand the base case, the recursive step, and how the call stack works. 13. Recursion can be a difficult concept to grasp and can make other topics like graphs, trees, and backtracking harder to understand. 13. Hash maps. These are very common and useful data structures that allow for efficient operations like adding, removing, and searching values in amortized O, 1, time 14. They are useful in many problems, including TWISM, and can be used as utility data structures for other algorithms such as DFS, recursion, and sliding window. 14. A good understanding of hash maps is essential for coding interviews. 17. What is a heap, and why is it useful? A heap is a tree-based data structure that comes in 2 variations, a min heap and a max heap. It's specifically designed to efficiently find the minimum or maximum value, respectively. Retrieving the min/max value takes O, 1, time. Adding or removing elements takes O, log n, time, where n is the number of elements in the heap. Importantly, building a heap from a pre-existing collection of n values can be done in O, n, time. Heaps are used in various algorithms, especially graph algorithms like shortest path calculations. How does the sliding window algorithm work, and what makes it efficient? The sliding window algorithm uses 2 pointers to iterate through an array or sequence, intelligently adjusting the window defined by those pointers to solve problems that might otherwise require nested loops and result in an O, n superscript 2, time complexity. By using 2 pointers that move through the data, the overall time complexity can be reduced to O, n. It's a technique that can be memorized and applied to various problems once understood. What is binary search and where does it fit in? Binary search is an efficient algorithm for searching a sorted list or array by repeatedly dividing the search interval in half. If the middle is the value you are looking for, you have found it. If not, you will either eliminate the top or bottom half. This method has a time complexity of O, log n, much more efficient than O, n, for large data sets. While straightforward in concept, identifying when to apply binary search isn't always obvious, requiring a deep understanding of when sorted data can be efficiently leveraged in a more complex problem. What are depth first search, DFS, and breadth first search, BFS, and why are they important? DFS and BFS are fundamental graph traversal algorithms. DFS explores as far as possible along each branch before backtracking, using a stack, often implicitly via recursion, while BFS explores all neighbors at the current depth before moving to the next depth using a queue. These algorithms are crucial because they form the foundation for many more complex graph algorithms and are frequently used in coding interviews. Mastery of DFS and BFS makes solving graph and tree-related questions much easier. Why is recursion such a crucial concept to master? Recursion is a powerful technique where a function calls itself within its own definition. Understanding the base case, where the recursion stops, and the recursive step is vital. Recursion is used in various algorithms, including DFS, backtracking, and some dynamic programming solutions. Recursion uses memory, specifically the call stack, so that needs to be taken into account. The concept itself is often challenging to new programmers, and it is important to grasp to understand many other more complex data structures and algorithms. Why are hash maps considered essential for coding interviews? Hash maps are a key data structure due to their ability to perform insertion, deletion, and lookups in amortized, constant time, O(1). They can solve problems that would otherwise take O(n) time. Hash maps are also useful as auxiliary data structures within more complex algorithm solutions, even where they do not solve the entire problem themselves. A solid grasp of hash maps and their efficiency is essential for coding interviews, as they form a building block for a large range of efficient solutions. What is the time complexity for building a heap? If all the elements are available at the start, a heap can be built in O(n) time. However, if elements are added to the heap one by one, each addition taking O log n time, the overall process of adding n elements will be O(n) log n time. What kind of problems are ideal for binary search and what are the potential challenges? Binary search is ideal for problems where you need to find a specific value in a sorted array or list. The classic example is just searching for an element. While conceptually simple, the challenge lies in identifying problems where the efficient search is not immediately obvious. This requires experience and careful consideration of what is being searched as well as what data structure is required for the situation. Overview. This solution guidance helps you deploy extract, transform, load, ETL, processes and data storage resources to create Insurance Lake. It uses Amazon Simple Storage Service, Amazon S3, buckets for storage, AWS Glue for data transformation, and AWS Cloud Development Kit, CDK, pipelines. The solution is originally based on the AWS blog Deploy Data Lake ETL jobs using CDK pipelines. The best way to learn about Insurance Lake is to follow the quick start guide and try it out. The Insurance Lake solution is comprised of two code bases, infrastructure and ETL. Specifically, this solution helps you to deploy a 3CS, collect, cleanse, consume, architecture Insurance Lake. Deploy ETL jobs needed to make common insurance industry data sources available in a data lake. Use PySpark Glue jobs and supporting resources to perform data transforms in a modular approach. Build and replicate the application in multiple environments quickly. Deploy ETL jobs from a central deployment account to multiple AWS environments such as dev, test, and prod. Leverage the benefit of self-mutating feature of CDK pipelines. Specifically, the pipeline itself is infrastructure as code and can be changed as part of the deployment. Increase the speed of prototyping, testing, and deployment of new ETL jobs. Contents. Cost. Sample cost table. Quick start. Python/CDK basics. Deploy the application. Try out the ETL process. Next steps. Deployment validation. Cleanup. Architecture. Collect, cleanse, consume. ETL. Well-architected pillars. Security. Infrastructure code. Application code. Online documentation. Additional resources. Authors. License summary. Cost. This solution uses the following services: Amazon S3, AWS Glue, AWS Step Functions, Amazon DynamoDB, AWS Lambda, Amazon CloudWatch, Amazon Athena, and AWS Code Pipeline for continuous integration and continuous deployment, CI/CD, installation only. An estimated cost for following the Quick Start and Quick Start with CI/CD instructions, assuming a total of 8 Glue DPU hours and cleaning all resources when finished, your cost will not be higher than $2. This cost could be less as some services are included in the free tier. We recommend creating a budget through AWS Cost Explorer to help manage costs. Prices are subject to change. For full details, refer to the pricing webpage for each AWS service used in this solution. Sample cost table. The following table provides a sample cost breakdown for deploying this guidance with the default parameters in the U.S. East, Ohio, region for 1 month with pricing as of October 2, 2024. AWS service. Dimensions. Cost USD. AWS Glue. Per DPU hour for each Apache Spark or Spark streaming job, build per second with a 1-minute minimum. $0.44. Amazon S3. Per GB of storage used, frequent access tier, first 50 TB per month. Put, copy, post, list requests, per 1,000 requests. Get, select, and all other requests, per 1,000 requests. $0.023. $0.005. $0.0004. Amazon Athena. Per TB of data scanned. $5.00. Amazon DynamoDB. Per GB month of storage, over 25 GB. Per million write request units, WRU. Per million read request units, RRU. 25 cents. $1.25. $0.25. Quick start. If you'd like to get started quickly transforming some sample raw insurance data and running SQL on the resulting dataset, and without worrying about CI/CD, follow the steps in this section. Python/CDK Basics. Open the AWS console in the US East 2, Ohio, region. Note, Insurance Lake uses US East 2 by default. To change the region, refer to the Quick Start with CI/CD. Select Cloud Shell at the bottom of the page and wait for a few seconds until it is available for use. Ensure you are using the latest version of the AWS SDK for Node.js and AWS CDK. sudo npm install GAWS lib AWS CDK. Clone the repositories. Git clone https://github.com/aws-solutions-library-samples/aws-insurance-lake-infrastructure.git. Git clone https://github.com/aws-solutions-library-samples/aws-insurance-lake-etl.git. Change the working directory to the location of the infrastructure code. cd AWS Insurance Lake Infrastructure. Create a Python virtual environment. In AWS Cloud Shell, your home directory is limited to 1 GB of persistent storage. To ensure we have enough storage to download and install the required Python packages, you will use AWS Cloud Shell's temporary storage, located in /tmp, which has a larger capacity. Python 3 mvenv/tmp/dutvenv. Activate the virtual environment. sars/tmp/dutvenv/bin/activate. Install required Python libraries. Note, you may see a warning stating that a newer version is available. It is safe to ignore this for the quick start. Pip install our requirements.txt. Bootstrap CDK in your AWS account. CDK Bootstrap. Deploy the application. Ensure you are still in the AWS Insurance Lake Infrastructure directory. Deploy infrastructure resources in the development environment, OneStack. CDK deploy dev insurance lake infrastructure at pipeline/dev/insurance lake infrastructure S3 bucket zones. Review and accept AWS Identity and Access Management, IAM, credential creation for the S3 bucket stack. Wait for deployment to finish, approximately 5 minutes. Copy the S3 bucket name for the collect bucket to use later. Bucket name will be in the form, dev insurance lake-AWS account ID-region collect. Switch the working directory to the location of the ETL code. cd/AWS Insurance Lake ETL. Deploy the ETL resources in the development environment, 4 stacks. CDK deploy dev insurance lake ETL pipeline/dev/insurance lake ETL DynamoDB dev insurance lake ETL pipeline/dev/insurance lake ETL glue dev insurance lake ETL pipeline/dev/insurance lake ETL step functions dev insurance lake ETL pipeline/dev/insurance lake ETL Athena helper. Wait for approximately 1 minute for DynamoDB deployment to finish. Review and accept IAM credential creation for the AWS Glue jobs stack. Wait approximately 3 minutes for deployment to finish. Review and accept IAM credential creation for the step functions stack. Wait approximately 7 minutes for deployment of step functions and Athena helper stacks to finish. Try out the ETL process. Populate the DynamoDB lookup table with sample lookup data. Resources/load_dynamod_lookup_table.py synthetic general data dev insurance lake ETL value lookup resources/synthetic general_lookup_data.json. Transfer the sample claim data to the collect bucket. AWS S3 CP resources/synthetic general claim data.csv/s3/collect S3 bucket/synthetic general data/claim data/. Transfer the sample policy data to the collect bucket. AWS S3 CP resources/synthetic general policy data.csv/s3/collect S3 bucket/synthetic general data/policy data/. Open step functions in the AWS console and select dev insurance lake ETL state machine. Open the state machine execution in progress and monitor the status until complete. Open Athena in the AWS console. Select Launch Query Editor, and change the workgroup to Insurance Lake. Run the following query to view a sample of prepared data in the consume bucket. Select asterisk from synthetic general data_consume.policy data limit 100. Next steps. Take the Insurance Lake Deep Dive workshop. You may skip to the Modify and Test to Transform step, as the prior steps overlap with the Quick Start instructions. Try out loading your own data. Try the Quick Start with CI/CD. Dive deeper with the included user documentation. Contact your AWS account team for a solution deep dive, workshops, or AWS professional services support. Deployment validation. Transfer the sample claim data to the collect bucket, source system, synthetic data, table, claim data. AWS S3 CP resources synthetic general claim data.csv S3 collect S3 bucket synthetic general data claim data Transfer the sample policy data to the collect bucket, source system, synthetic data, table, policy data. AWS S3 CP resources synthetic general policy data.csv S3 collect S3 bucket synthetic general data policy data Upon successful transfer of the file, an event notification from S3 will trigger the state machine trigger Lambda function. The Lambda function will insert a record into the DynamoDB table environment resource name prefix etal job audit to track job start status. The Lambda function will also trigger the step function's state machine. The state machine execution name will be filename -YYYYMMDDHHMMSSXXXXXX and have the required metadata as input parameters. The state machine will trigger the AWS Glue job for collect to cleanse data processing. The collect to cleanse AWS Glue job will execute the transformation logic defined in configuration files. The AWS Glue job will load the data into the cleanse bucket using the provided metadata. The data will be stored in S3 as S3 environment resource name prefix account region cleanse synthetic general data claim data year equals YYYY month equals day equals DD in Apache Parquet format. The AWS Glue job will create or update the data catalog table using the table name passed as a parameter based on the folder name, policy data and claim data. After the collect to cleanse AWS Glue job completes, the state machine will trigger the cleanse to consume AWS Glue job. The cleanse to consume AWS Glue job will execute the SQL logic defined in configuration files. The cleanse to consume AWS Glue job will store the resulting dataset in S3 as S3 environment resource name prefix account region consume synthetic general data claim data year equals YYYY month equals day equals DD in Apache Parquet format. The cleanse to consume AWS Glue job will create or update the data catalog table. After successful completion of the cleanse to consume AWS Glue job, the state machine will trigger the etal job auditor Lambda function to update the DynamoDB table environment resource name prefix etal job audit with the latest status. An Amazon Simple Notification Service, Amazon SNS, notification will be sent to all subscribed users. To validate the data load, use Athena and execute the following query. Select asterisk from synthetic general data consume.policy data limit 100. Cleanup. Refer to the quick start cleanup instructions. Architecture. This section focuses on the overall Insurance Lake architecture and the components of the ETL. Collect, cleanse, consume. As shown in the figure below, we use S3 for storage, specifically 3 different S3 buckets. Collect bucket to store raw data in its original format. Cleanse/curate bucket to store the data that meets the quality and consistency requirements for the data source. Consume bucket for data that is used by analysts and data consumers, for example, Amazon QuickSight, Amazon SageMaker. Insurance Lake is designed to support a number of source systems with different file formats and data partitions. To demonstrate, we have provided a CSV parser and sample data files for a source system with 2 data tables, which are uploaded to the collect bucket. We use Lambda and step functions for orchestration and scheduling of ETL workloads. We then use AWS Glue with PySpark for ETL and data cataloging, DynamoDB for transformation persistence, and Athena for interactive queries and analysis. We use various AWS services for logging, monitoring, security, authentication, authorization, notification, build, and deployment. Note, AWS Lake Formation is a service that makes it easy to set up a secure data lake in days. Amazon QuickSight is a scalable, serverless, embeddable, machine learning-powered business intelligence, service built for the cloud. Amazon Data Zone is a data management service that makes it faster and easier for customers to catalog, discover, share, and govern data stored across AWS, on-premises, and third-party sources. These 3 services are not used in this solution but can be added. ETL. The figure below represents the ETL resources we provision for the data lake. A file server uploads files to the collect bucket of Insurance Lake. File server is a data producer or source for the data lake. S3 triggers an object-created event notification to Lambda function. The Lambda function inserts job information in a DynamoDB table. The Lambda function starts an execution of step function's state machine. This step runs the first AWS Glue job, initiates data processing from collect to cleanse. An AWS Glue job will process the data from collect to cleanse. Source data is assumed to be in CSV format and will be converted to Parquet format. DynamoDB stores original values from PII tokenization and provides lookup data to the AWS Glue job. After creating Apache Parquet data, the job updates the AWS Glue data catalog table. In this step, the second AWS Glue job initiates data processing from cleanse to consume. The AWS Glue cleanse to consume job fetches data transformation rules from AWS Glue ETL scripts bucket and runs transformations. The AWS Glue job stores prepared data in Apache Parquet format in the consume bucket. The AWS Glue job updates the AWS Glue data catalog table. The AWS Glue job updates the DynamoDB table with job status. Step functions sends an SNS notification. Data engineers or analysts analyze data using Athena. Security. For more information on how AWS services come together in Insurance Lake to align with the security pillar of the AWS well-architected framework, refer to the Insurance Lake well-architected pillar alignment for security. Infrastructure code. Insurance Lake uses CDKNAG to confirm AWS resource security recommendations are followed. CDKNAG can generate warnings, which may need to be fixed depending on the context, and errors, which will interrupt the stack synthesis and prevent any deployment. To force synthesis of all stacks, including the code pipeline deployed stacks, which will check all code and generate all reports, use the following command. cdksynth. When this operation is complete, you will also have access to the CDKNAG reports in CSV format in the cdk.out directory and assembly directories. By default, the AWS Solutions Rules Pack is used, but any combination of CDKNAG rules packs can be selected by adjusting the source code in 4 locations, 2 for both the infrastructure and ETL code bases. Infrastructure app.py line 21, ETL app.py line 20. Hashtag enable CDKNAG for the mirror repository, pipeline, and related stacks. Hashtag environment stacks must be enabled on the stage resource. cdk.aspects.of, app.add, AWS Solutions checks. Infrastructure pipeline underscore stack.py line 148, ETL pipeline underscore stack.py line 147. Hashtag enable CDKNAG for environment stacks before adding to. Hashtag pipeline, which are deployed with code pipeline. cdk.aspects.of, pipeline underscore deploy underscore stage, .add, AWS Solutions checks. Application code. Insurance Lake uses Bandit and Amazon Code Guru for static code analysis of all helper scripts, Lambda functions, and PySpark Glue jobs. To configure Code Guru code reviews, follow the AWS documentation on creating code reviews. To scan all application code using Bandit, use the following command. Bandit reni.bandit. Additional resources. Insurance Lake documentation. Insurance Lake Quick Start AWS Workshop. Insurance Lake Deep Dive AWS Workshop. General Insurance Dashboard on QuickSights Demo Central using consume-ready data. Life Insurance Dashboard also on QuickSights Demo Central. AWS Solutions Library Guidance for Modern Insurance Data Lakes. Insurance Lake in the AWS Well-Architected Framework Financial Services Industry Lens. G. Data Pipeline Architecture Diagram. Selecting a data pipeline architecture involves choosing one or multiple architectures to meet specific requirements. Let's look into the types of data pipelines to help you make an informed choice. ETL. The ETL data pipeline architecture became predominant in the Hadoop era, which roughly lasted from 2011 to 2017. In ETL, you extract data from various sources, transform it according to your operational needs, and load it into a destination system for analysis and reporting. Common destinations for ETL pipelines include data warehouses, databases, ByTools, and cloud storage solutions. ELT. The ELT data pipeline architecture has been gaining popularity since 2017. It is particularly beneficial if you deal with large datasets or uncertainty about data handling. With an ELT data pipeline, you extract data, load it into your preferred destination, and transform it later according to requirements. This gives you more control and flexibility to handle your data. The associated benefits include higher computing speed, agility, and reduced costs for advanced analytics. Stream processing data pipeline. Streaming data pipelines involve continuous ingestion and processing of data streams in real time or near real time. This involves capturing events at the source as they occur and loading the events into the destination system with millisecond-to-second latency. You can utilize streaming data pipelines to perform enhanced transformations and analysis, especially for machine learning and data science. Tools like Apache Kafka facilitate stream processing of data with high throughput and low latency. The data is then directly loaded into destinations such as transactional systems and real-time dashboards. Batch processing data pipeline. A batch data pipeline processes massive amounts of data at regularly scheduled intervals or batches rather than in real time. Batch data pipelines can take hours or even days to execute, especially for large data sizes. Hence, these pipelines are often scheduled to run during off-peak hours when user activity is low. This is an efficient solution when you don't require immediate or real-time data processing.
Where's the box?
Right there. Oh,
So here's the thing.
I know how to do it. Are you?
Yeah, put it in. Here, I'll break it.
Just slap it. Hey, let me mix it. For 2 minutes. Wait, don't mix it right yet. Let me set the 2-minute timer and set it for doing it right. Hey, Google, set a timer for 2 minutes. Oh, we have to mix it for 2 minutes.
We're not doing it by hand. We're going to do the machine.
Hey, Google. Yes. I said it. Your positive power. Yeah, so that's what we do.
How many minutes?
It took 2 minutes. I started. Daddy, look. I know. No. It said it's okay now.
Okay.
And I can smell it. I can smell it.
Now,
See?
this is too big. It'd be better to do this.
Okay, let's.
It would turn out better.
Okay. Whatever you say, Mr. Cricket. Hey, yo. You say that. What's wrong with this?
Now we gotta put some oil in the
We
bottom.
already did it.
No, inside the bottom of the ice cream.
Yeah, can't you? First, read the instructions. Look, read number 2. Read number 2.
Now to keep the thing from sticking. It's like,
No, it said it says heat over to. It says oh. It said if it's a non-stick pan, you put it. I'll do it. Hey Google, stop. I never said anything like that. Just saying.
trust me, this one is pretty good.
Next time I'll know how to trick. There's no instructions. Just got it.
Now, both of you, pour the mix inside the bowl.
It doesn't say how like. Oh man, we forgot to get this.
Get that spoon and scoop this over the onions. See how it's a lot still in it?
I don't know when it says bacon minutes. I don't know when it says to cook.
Let me tell you.
What does it say? Change.
Oh, okay. This is a 13 by 9.
You know that.
Yeah. Um, 27 minutes. And use the reset button.
watch something.
Processing.